Alright, very good day to you. Today we are looking at chapter 8.1, carbon lattices. 8.1 carbon lattices. You need to look at page number 178. So this slide is on the abundance and properties of carbon. When we talk about carbon, we know that carbon has a chemical symbol of C, and it says it is the 11th most abundant element. So based on what you do every single day, the food that you consume contains glucose, it consists of carbon, and the air that you breathe out contains carbon as well in the form of carbon dioxide. So it says here carbon has 3 isotopes. It means that they have different mass number but the same atomic number, which means the number of electrons and the number of protons is the same, but what has changed here is the number of neutron, which is why the mass number changes. So as you probably aware as well, carbon, you have carbon 12, carbon 13, carbon 14. Carbon 12 is the most abundant, and when you do your calculation on the isotopic abundance, you'll find that the relative mass number of carbon is very close to carbon 12. It's 12.0 something. It's very close to carbon 12 because the most abundant element here is carbon 12 of the 3 different isotopes. So has one of the highest melting points of any element and the sublimation, changing from solid to gas at temperatures above 3550 degrees Celsius. Is a non-matter, but a number of forms can conduct electricity, can form single, double, and triple covalent bonds, can form large molecules and lattice structure by bonding to itself. Alright, so these are the general idea of carbon, and carbon usually forms covalent molecules, and we have discussed these covalent molecules through the covalent bonding. So if it's a single covalent bond, it means that it's sharing 1 valence electron, double covalent bond sharing 2 valence electron, triple covalent bonds sharing 3 valence electron. So I'm going to move on to the next slide. So what we are focusing on today, we are talking about allotropes. What are allotropes? Allotropes are different physical forms of the same chemical element, but exist while in the same physical state, solid, liquid, and gas. So today we will be focusing on the allotropes of carbon, but before we move into it, allotropes also applies to some other elements such as oxygen, phosphorus, besides carbon. So there is a brief paragraph here in your textbook on oxygen. Oxygen do form allotropes. What does it mean? If you look at these two structures here, we have oxygen gas and we have ozone. Ozone is basically the ozone layer that we have in the atmosphere. We know that oxygen has a formula of O2. Ozone has a formula of O3. So these are the covalent molecule. If I highlight these at the bottom, you can see that the molecule, the first molecule here is O2, oxygen. You can see there's double bond. It means that both oxygen is sharing 2 valence electrons with the other oxygen. And the second diagram shows that you have 1 single bond and 1 double bond. Eventually, each oxygen atom within this ozone will have 8 valence electron. Okay, so the point here is that both of these, they are allotropes of oxygen. So they are of the same chemical element, but they exist as different physical forms. Alright, same physical state, same chemical elements, but exist as different physical forms. So an example here would be oxygen. We exist as oxygen gas and ozone. I said both of these contains only oxygen atom, which is why they are known as allotrope, which means that if that particular element has a mixture of with other elements, that is known as allotrope, and allotrope has to be of the same element. So in this case, oxygen exists as oxygen gas and ozone. Both of them consist of oxygen atoms only. So I'm going to move on to the next slide, and we are going to talk about carbon, mainly carbon for today. Moving on to the next slide. Alright, allotropes of carbon. So the 3 most common allotropes of carbon are diamond, graphite, and amorphous carbon. They are also different. Two other main forms of carbon allotropes that we're going to discuss in the next few lessons. But now we are focusing on diamond, graphite, and amorphous carbon. It says these have multiple applications. The two-way structure and bonding affects the physical properties and attributes. So we have graphite, we have diamond, we have fullerene. And what you can see here, each of these elements consists of carbon atoms only, but different physical forms. There are different physical forms of carbon elements. So I'm going to move on to the next slide. Alright, so we have diamond. As you can see, diamond, you have 1 carbon being bonded to 4 other carbon atoms, as you can see here. So 1 carbon bonded to 1 carbon atoms, 2nd carbon atoms, 3rd carbon atoms, and the 4th carbon atoms. And it says here they are very hard, sublimes, non-conductive, brittle. So if you talk about diamond, generally they are very hard, and that is the reason why they are used for jewelry, cutting tools, and drills. So they are used in equipments that cut rods because they are very, very tough. If you're looking at graphite here is a different physical form of carbon, but what you have here, instead of one carbon being bonded to 4 other carbons, you have one carbon being bonded to 3 other carbons. Some carbons are bonded to 2, as you can probably see. But in general, what you will get, and it's stated here, covalent layer lattice, each carbon bonded to 3 other carbon atoms, 1 delocalized electron per carbon atom. There's something called a delocalized electron. Delocalized electron means the electron is in a way dangling on the surface of the carbon. So because if you're probably aware as well, carbon is in group folding, it has 4 valence electrons. So if one carbon is being bonded to 3 other carbons, technically some of these carbons do have delocalized electrons. It's very similar to what we have discussed about sea of delocalized electron in metal compounds, but they are different because in metal compounds you're talking about metal elements. In this case, you're talking about non-metal elements. They have that delocalized electron because the electron is not bonded in any way. So you can see that graphite here is conductive, it's slippery, soft, and greasy. You must understand why it is conductive. It is conductive because of the presence of the delocalized electron, and that delocalized electron is not found in diamond. Graphite is a lot weaker as compared to diamond, so they're used in pencil electrodes, reinforcing fibers, and lubricants. If we talk about amorphous carbon, we talk about amorphous carbon shown by the irregular structure of carbon atoms, not of a particular shape. So many varieties with many different non-continuous packing arrangements. Say they are conductive, non-crystalline, and they're cheap. Printing ink, carbon black filler, activated charcoal, and photocopying, they use amorphous carbon. Moving on to the next slide. Alright, so diamond. As mentioned before, once again, when we talk about diamond, you have one carbon be bonded to 4 other carbon atoms. One carbon atom be bonded to 4 other carbon atoms, and you get what we call a covalent network lattice structure. A lattice covalent or covalent lattice structure is different from a simple covalent molecule. So diamond here will be very different from carbon dioxide or carbon monoxide because it is a giant lattice structure. Diamond is a giant lattice structure. They do not have any weak intermolecular forces present, any strong covalent bond. As you can see in this diagram, there is no intermolecular force. All of them are bonded to one another using covalent bond, which means they are very hard, very strong, and they have very high melting point as a result. And you know the atoms are held firmly together. So if you have been asked a question why diamonds are hard, you need to be able to understand that because the atoms are held firmly together in a fixed position in the lattice structure. Moving on to the next slide. Alright, once again, there's many other explanations on diamonds. So it says here, single covalent bonds between carbon atoms are strong bonds. The entire structure of diamond consists of continuous network of these bonds. We have discussed this, making them very high and rigid. There are no small molecules in diamonds, so there are no weak forces between the atoms. There are only strong covalent bonds between carbon atoms, and this means the sublimation point very high. The rigidity means that diamonds are brittle and break rather than bend. Diamond does not conduct electricity because it does not contain any charged particles. Because the atoms in diamonds are held together very strongly, the thermal conductivity is extremely high. It's 5 times greater than that of copper, leading to some specialty electronic uses where diamond is used to transfer heat away from some important electrical components. So what you need to get off this slide is that when we talk about diamond, we know they are very strong because each carbon atom is being bonded to 4 other carbon atoms. They do not have intermolecular forces. They only have strong covalent bond, which means that if you try and push it or put pressure on diamond, it will probably break. But at the same time, it's strong because of the covalent bond, which is why you can use diamond for cutting equipment. And here, diamond do not conduct electricity because they do not contain charged particles. They can freely move. Alright, moving on to the next slide. Alright, I'm just going to continue with the second allotrope of carbon. So we have discussed diamond. Today we are looking here we are looking at graphite. It says graphite is a different form of carbon. The carbon atoms of graphite are in layers, and so there are strong covalent bonds between the carbon atoms in each layer. The layer never structure contains delocalized electrons. However, there are weak dispersion forces between the layers. As a consequence, it's hard in one direction but quite slippery and soft in the other direction. The structure of graphite is referred to as covalent layer lattice. When we talk about diamond, we are talking about giant covalent lattice structure. When we talk about graphite, we are talking about covalent layer lattice. So they are made of many different carbon being bonded together through covalent bond. But you have one layer, you have a second layer, and so on, which means that there is a tendency of graphite being a good electrical conductor because it has that delocalized electron. I'll show you on the next slide. So if I look at this slide here, you have one layer which is at the top. So let's just say that you have the first layer. So just let me show you this. So let's say this is your first layer, this is your second layer, this is your third layer, and this is your fourth layer. And what you can see is that each layer consists of carbon being bonded to 3 other carbon atoms through strong covalent bond, and each layer is being separated one after another, and we have that weak dispersion forces that exist between layers because of the presence of the delocalized electron as well. So I'll show you on the next slide. So as you can see here, when we talk about graphite, they have different properties from diamond. Even though both diamond and graphite are made of carbon, the reason for that is because graphite consists of carbon being bonded to 3 other carbon atoms through covalent bond. At the same time, it is able to conduct electricity because of presence of the delocalized electron, and there's dispersion forces that exist between them. And we talk about dispersion forces, we did discuss this in the last chapter. It is a type of intermolecular force that exists in a non-polar molecule. In this case, this is a non-polar molecule or non-polar structure, and it does contain dispersion forces. So the covalent bonds between the atoms in layer experience the graphite resistant to heat. It sublimes at very high temperature, 3600 degrees Celsius. Each carbon atom is bonded to 3 other carbon atoms. The 4th valence electron from each atom is able to move within the layer. It says the electrical conductivity of graphite is due to these delocalized electrons. So the conductivity of graphite makes it suitable for application of battery electrons where conductivity is required but metal is not suitable. So you can use graphite to create these materials, in this case the battery electrodes, but you cannot use diamond because diamond, even though once again it is an allotrope of carbon, in terms of the presence of carbon, it is present in both diamond and graphite. They solely consist of carbon only, but when we are talking about graphite, it contains that delocalized electrons. Moving on to the next slide. So we are almost towards the end. Now we are talking about amorphous forms of carbon. As mentioned before, when we talk about amorphous form of carbon, we're talking irregular shape. So the irregular shape carbon, there is no one particular structure, and then there's 2 main types of amorphous carbon. We have charcoal, we have carbon black. Amorphous carbon contain irregularly packed tiny crystals of graphite and other non-uniform arrangement. It said lumps of charcoal are produced for use as a fuel, and while carbon black is used to make printer toner ink. So these are the 2 main examples. We have charcoal and we have carbon black. So we are talking about charcoal is used for fuel, oil, and carbon black is used for printer toner ink. Moving on to the next slide. Alright, so it says amorphous carbon can be formed from the combustion of wood and other plant material while there is a limited supply of air. There are several other types of amorphous carbon, including soot being emitted from the industrial chimney. The distinction between the different forms of carbons are blurred. There is no clear distinctions of that amorphous carbon, but in general, amorphous carbons can be formed if there's combustion of wood, but with very limited supplies of oxygen. That means, so instead of carbon reacting with oxygen to form carbon dioxide, your carbon will remain as carbon because the oxygen is not present. So the end product, you will have that soot products which is being released, and this particular product is an allotrope of carbon, but it is of an irregular shape. unlike what we have seen with diamond, graphite, and fullerene. Going on to the next slide. So use of carbon black. It says carbon black is a refined type of amorphous carbon in which the particle size is more uniform. Most carbon black is used to reinforce rubber products such as tires, hoses, causing their black appearance. The surface interaction between the fine carbon particles and the rubber molecules increases the strength and toughness of the product. Many printer and photocopier toners contain carbon black particles mixed with the binder, polymer, and other additive. So what you need to get out of this slide is that when we are talking about carbon black, and if you have a printer at home, or if you do use a photocopier, try and have a touch on the paper itself, the printer paper. You will find that those black ink that you see on the paper is actually made of carbon black, which is an allotrope of carbon itself. Going on to the next slide. So, activated charcoal. So, charcoal can be activated by heating it to high temperatures in the presence of an inert gas. When we talk about inert gas, we're talking about noble gases, those group-eating gases. For example, we talk about helium, we talk about xenon, those argon, those are examples of inert gases. It says activated charcoal particles are so porous that it's estimated 1 gram sample has a surface similar to that of an Australian rules football oval. There's a diagram on the textbook that shows how porous it is. And when we're talking about activated charcoal, they say they can absorb. Once again, absorb means that it will be on the surface instead of going into the material itself. We have discussed the difference between absorption and absorption. Absorptions with a D and absorptions with a B are two different terms. When we're talking about absorption, it will be on the surface of that particular material. Absorption will be into or getting absorbed into the material itself. So in this case, absorption of charcoal will be on the surface. And you see the impurities are trapped in the pores of the activated charcoal particles by weak attractive forces such as dispersion forces. This makes activated charcoal useful for water filters, although cattle, insects in shoes, a treatment for drug overdose. Activated charcoal is pumped into the breathing stomach to absorb the harmful drug molecules. Bear in mind, when we are talking about absorption, it will be on the surface of the material. It is useful if the material has large surface area, and this is what you have seen with these activated charcoal particles. They have very large surface area and is good for it to absorb materials. In this case, these are the uses that they have been used: water filters, odor, cattle, inserts in shoes, and treatment for drug overdose. So make sure that you do the questions now on the school board page. So do complete the questions on the school board page for chapter 8.1. So we have looked at basically the different allotropes of carbon. And we are talking about allotropes. We are talking about the different forms of that particular element. And the allotropes of carbon, there's three main types. We have diamond, graphite, and we have fullerene. And we have also been talking about the irregular shaped carbon in the form of activated charcoal and in the form of carbon black. So do complete the questions, and then we will discuss this in class and when I see you in the next lesson. Alright, thank you very much.